Today we're going to do a ballistic pendulum lab. Ballistic pendulum lab is a lab that focuses on conservation of energy and conservation of momentum. We'll study both of these topics in this lab. We're going to do two distinct experiments related to two different velocities. The equipment that we're going to be using can be seen here. With this equipment, we have an arm, which is located here. We have a projectile launcher. We are going to be using a photo gate. We will also have a projectile ball. Let's get the data collected, and I'll explain to you how the equipment works as we're doing this. So the first thing that we need to do is measure out some of the masses. So I have here a balance, and I'm going to place on there the projectile ball. And we're going to find that the projectile ball has a mass of 65.97 grams. So the value of the ball is 0.06597 kilograms. The arm's mass, this is the arm, and you'll see how that works, is 248.02 grams. So 0.24802 kilograms. Now the mass of the projectile and the arm are going to be the same in both of our trials. So I've just copied those over. The arm, when it's in its position, will also have an initial height of 0. We're going to set the arm and the ball together. We're going to refer to the arm and the ball together as the system. There's a point where we were just talking about the arm. There's a point where we're just talking about the ball. Together, they're the system, and we're going to start them off at the same height. We're going to treat that as our 0 mark. So our initial height of those will be 0. So we are now going to measure the initial velocity of our projectile. And to do that, we're going to use the Pasco system like we did previously to calculate out the velocity. And so I have this already set up in the system where I've attached the photo gate to the Pasco. In this case, we're using a USB link, USB'd into the computer, and I am going to place the ball in the projectile launcher, push it back one click, and make sure the ball is seated in the back of the launcher. And I am going to hit the record button, and when I do, it will start a timer. When the ball is fired out of the projectile launcher, it'll pass. There are two distinct photo gates on here. It'll pass photo gate 1. It'll identify that time. It'll pass photo gate 2. It'll identify that time. Take the difference in those times. It knows the distance between those two lasers, and then it calculates out velocity using the displacement divided by the time. And so since the lasers are interrupted, starts and stops the clock, or identifies the time that on the clock, what we will then be able to do again is calculate the velocity of the projectile as it leaves the launcher. And so I have it set up. I am going to hit record. I'm going to reach over and grab the string. We'll pull the string, releasing the ball. You can see here that the velocity is 3.5 meters per second. I've done this experiment a number of times and can tell you that that is the correct velocity. I wanted you to be able to see how it's done. I'm not going to do multiple trials on this. So our initial velocity for the trial 1 is going to be 3.5 meters per second. Sorry, that's the arm. I wrote that in. The ball is going to be 3.5 meters per second. The second trial, the second trial that we're going to be doing here is going to be taking the ball and it's going to be pushing it back a little bit further. So now we're going back 1 click, 2 clicks, 3 clicks. Full velocity of the ball. We put that back in there. Again, I am going to reset my photo gates. I'm going to grab the string and lift. And I get about 6.93 meters per second. I'm going to do that one more time. That value is a little bit lower than I would have expected. I think the ball may not have been completely seated in the back. Sometimes it rolls forward a little bit. You have to be careful that it is seated correctly back there as we do this. Again, I've done this a number of times, so I have a pretty good idea what velocities we're looking for. About 7.6. That's the velocity that we're expecting. And if you're doing this here with me, what you're doing is you are finding that the ball is going to get fired a couple times by you to prove this. But again, I've done this outside this video. So 7.60 meters per second. I do want to make sure that I'm taking that out to the correct number of sig figs. So I'm going to click on Properties, Format Cells. Go. And I'm going to bring that number out to 2 decimal spots. And again, the reason I'm doing that is I want to make sure that this is recorded to the correct number of decimal spots to the measurements that we came up with here. Okay, so now that we've done that, I'm going to remove the equipment on here that is the photo gate system. We'll get that out of the way. We're not going to need that anymore. I am going to bolt the projectile launcher onto this so that it is completely in place. We're going to take the arm and we're going to place the arm, we're going to hang the arm on here so that it will swing. Now notice that the arm has on it a cup, and that this cup the ball will sit into, and the ball then will stay. You will see here there's a little lever that I can push to release the ball. If I put the ball up in there, it stays in there, creating a perfectly inelastic collision. Okay, so now I'm going to attach the arm. It just screws in up here. You'll notice this angle indicator. Notice the angle indicator, which will be used to calculate the angle. So as this arm swings up, the angle indicator goes with it, set to 0 degrees. When we swing it up, goes to whatever angle we it gets forced to, and then it'll fall back down, losing energy as it bounces off of here. So initially we're down here. We're going to take the ball. I'm going to set it in here before we get too far along, and I'm going to set it at the first click. Okay, and it's now down at the first click. Set my angle. And so what we are going to do is realize that initially the arm is not moving. Everything is sitting there at rest. So 0 meters per second. That's the same for both trials. And we're going to fire the projectile. So I come over, I grab the string, we fire. We then can come down and see that this is sitting at about 30, just at about 30, sorry, this is 20, 25, 26 degrees, right about 26 degrees. So probably need to mark that down here, that the angle of the arm is 26 degrees. And that was when we shot it at the lower velocity. Now, I'm going to release the ball and do that again and just verify that value. So we put the ball in. Again, I'm going to push it back one click. I move the angle indicator down to 0. I then take hold of the string. We fire. And it goes again to about 26 degrees, right at the same spot. 26 degrees is the angle of the arm. So what you're going to do is you're going to have to calculate the velocity of the system using the concept of a perfect inelastic collision. We know the mass of the projectile. We know the initial velocity of the projectile. We know the mass of the arm. We know the initial velocity of the arm. Once they collide, they are going to have a perfect inelastic collision, and you're going to be able to calculate out the velocity of the system afterwards. You also are then going to have to identify what the final velocity is. And so what you will do is realize that that is going to convert into kinetic energy. So as this swings back, the height of the ball has risen. I have a little picture here to help understand that concept. So the initial height is here, right down here, and this swings up and it gains a little bit of elevation. That elevation can be calculated because the energy of the system at the bottom, so we know the velocity of the system at the bottom, and so from there we could calculate out the energy, the kinetic energy of the system at the bottom, based on the fact that we know the velocity and the combined masses. So we could then insert that in here. Knowing the kinetic energy initially and realizing that the final velocity would be 0. When it gets to the top, we're able to realize that we're able to solve for the height because the kinetic energy initial becomes gravitational potential energy. And so we're able to solve that out for the height, doing our 1/2 mv squared is equal to mgh. The way we want to validate that, though, is by using this diagram here, where we're seeing that the height also refers to L cosine theta, which is the length of the leg of the triangle. We know the length of the rod, minus L cosine theta. And so what we need to be able to do is work our way backwards and solve for the height. That means that we do also need and if you probably are identifying that now, we also need the length of that rod, which we'll measure out here as well. And I'll do that at the end, and we'll put that piece of data in our table. So you're able to calculate the final height, and then you're able to calculate it again using the angle. So down here we'll use the angle to calculate the height. Up here we'll use energy to calculate the height. These two values are what we're going to compare for our error. Okay, we'll compare the final height that you got through calculations to the final value you got through the experiment, and then again some calculations. So let's put the ball in here and get our other piece of data. So now we've pushed it back all the way. Ball is seated at the back. We set our angle back to 0. And I'm going to fire. And this comes up to about 57 degrees. Do it again to validate that. Here we go, 57 degrees so I got the first time. That says 56. Let's do it just one more time, see which one of those is. We're very small difference, but just for the sake of not getting the same value, let's do it one more time. Here we go. Okay, that looks like 55 degrees. So let's go with 56 degrees. There, you could hear some energy with the sound and things being lost. There could be a little bit, but 56 degrees seems to be the measure we're going with. And again, you can calculate out these items. We do need that length. I'll pop this off of here again. And we'll measure the length of the system from the center of the ball to the back end. And that appears to be just about 30.5 centimeters. So the one value that needs to get in here to calculate that final height of the system is going to need to be the length of the arm and again that's going to be 0.305 meters, 30.5 centimeters, and we'll put that over here as well. So what you're going to do is you're going to calculate, again, the height of the system using the angle and the height of the system using the conservation of energy and momentum, and then you'll report that out as your instructor tells you to do so. If you have any questions, as always, please let me know. Have a wonderful day.